Yes. So, as Gustav Kirchhoff said, energy is a function of frequency and temperature. Wien performed experiments to try to develop an expression for energy in terms of those two. And he arrived at this equation: energy equals C1 lambda raised to minus 5 e to the power minus C2 by lambda t, where C1 and C2 are constants, T is the temperature, and lambda is the wavelength. Now we know Gustav Kirchhoff said energy is a function of frequency and temperature. Here, instead of expressing it in terms of frequency, Wien has expressed in terms of wavelength and temperature. And why is it not a problem? Because we know that the product of frequency and wavelength, nu lambda, is a constant. It is equal to 3 into 10 to the power 8. So if you have lambda, you can always replace it by 3 into that. If you have lambda, you can replace it as 3 into 10 to the power 8 divided by mu to get your equation in terms of mu. So that is not a big problem. So this is the expression he came up with. But what happened was, this person called Rubens proved that this expression holds true only for short wavelengths. In longer wavelengths, it fails. Then in the 1900s, two physicists called Rayleigh-Jeans, they came up with their own expression, again to relate energy with lambda and temperature. And we will not be looking at their exact expression, but it said energy is inversely proportional to the fourth power of lambda, meaning energy directly proportional to lambda raised to minus 4. So they came up with an expression of that sort. But then their expression also failed at short wavelengths. So what is happening here? There are two independent sets of physicists. Both are trying to find an expression for energy in terms of frequency and temperature, or wavelength and temperature. Each came up with one expression. Wien's expression works for short wavelengths but fails at long wavelengths. Rayleigh-Jeans expression works for long wavelengths but fails at short wavelengths. And if you want one reliable expression, then it should work across the entire spectrum of wavelengths, which none of them managed to develop. So that was the situation. And then Max it is important to note that all these people assumed that energy is continuous. So these expressions were developed under that assumption. And then Max Planck entered the picture. He made one assumption. He made the assumption that energy is quantized, meaning it can only take certain specific values. It is discrete. And with that assumption, he came up with a modified version of these expressions, which sort of combined both expressions. It combined Wien's as well as Rayleigh-Jeans, and it worked across all wavelengths, long, short, medium, everything. So that is the expression we are going to be studying.